Hello dear students. In today's lecture, we'll be looking into the mitigation of power quality issues. So the module goes like this. So initially we'll be having an analysis regarding how the harmonics can be eliminated, basically with the help of some filters, the passive filters, the active filters, as well as we'll have some hybrid filters also. Okay, and then specifically we'll be going through the sag as well as swell correction using DVRs, and then two power quality conditioners, DStatCom as well as UPQC. So we'll be looking into the circuit diagrams as well as the working, and we'll analyze how these two devices help in mitigating the power quality issues. So the first part is concentrated towards harmonic elimination, where the filters can be used or placed to eliminate the harmonics. Now, when we are planning for any installation, we have two options with us. One is uh, we can plan the devices so that the devices can plan or choose the devices in such a way that it produces minimum level of voltage distortion. Okay, so this can be uh, done by basically controlling the power electronic switches properly, so that the amount of harmonics which are injected uh, into the system or into the rest of the system can be eliminated. Or you can also think about installing harmonic compensation equipments at the uh, device terminals. So this is a second method. So once you are not able to completely eliminate the harmonic with the help of choice of your working equipment, you can always think about installing some compensation devices or elimination devices which supports harmonic reduction and elimination. Okay, and the external harmonic suppression can be done with the help of these filters, and the filters can be installed near to the point of distortion, and this filters basically make sure that the harmonic current is not interacting with rest of the system, and it is limited to the that location where it is being generated. And the filters can work in two ways. It can provide a bypass for the harmonic currents. This is one way. Or it can block the movement or flow of harmonic currents from one point to the other or entering the system. Or it also can compensate by supplying harmonic currents or voltages locally. So the harmonic needs can be suppressed by either bypassing the harmonic currents, blocking them, or providing or compensating them locally. And the filters can be classified into the passive, active, as well as the hybrid filters. Now, these are some of the factors that affect the choice of filters. So the main factors that needs to be considered includes the power as well as the voltage rating of the equipment to be installed, the effect of internal waveform distortion on rest of the plant that needs to be considered, the number as well as the type of elements, whether you are using one, two, or uh, uh, and large number of elements. In the of energy storage elements, the order of the filter also increases, and whether you are going for an active or a passive filter. And the topology is also very important, whether you are going to choose a shunt filter or a series filter. If it is a shunt filter, it basically provides high impedance for the low impedance for the harmonic current, so that the particular harmonic will be shunted. And if it is a series kind of topology, it provides a, or it offers a high impedance to the flow of that particular frequency. So in that way, you are able to eliminate the harmonics by using shunt, and the choice between shunt or series, or even a combination of both. Then you'll also have to think about or consider the supply system, whether it is a single phase or a three-phase system, the power rating, and the variable which you are going to compensate, whether it's a current voltage, reactive power, or whether you're trying to balance the phase, what is the nature of activity that you're going to do in order to eliminate the harmonics. So that needs to be identified. and the converter type, if it is a type of hybrid converters or like UPQC and this STATCOM, that will be using some power electronic devices. So the type of converter that can be used, and in case of inverters, the control technique as well as the reference current generation methods, which are generally in use, ID, IQ, such you'll be generating the reference currents in DQ frame. So such type of current generation methods also needs to be considered when you're trying to choose a filter. And the most common or the basic type of filter is the passive filter, and you're going for the active filter as well as hybrid filter, and the filter becomes more complicated and more control has to be done. Now the passive filter basically provides a low impedance path for the harmonic signals, and you have two types of passive filters. One is a shunt passive filter, and then you have the series passive filter, and you have a combination of series and shunt together. And then you can also have the active filter. This active filter will be injecting harmonic signals which are 180-degree out of phase with the harmonic signals present in the system, thereby eliminating them. So you can have such type of filters like again series shunt LSI, as well as a combination of series and shunt. UPQC falls under this active filter, and then you have a combination of active and passive filter, which can be termed as the hybrid filter. Now, the most common type is, and the simplest one is a passive filter. This passive filter is basically a combination of passive elements, including the capacitors, inductors, as well as resistors. And these energy storage elements, capacitors, as well as inductors, are tuned to resonate at a single frequency or even a band of frequencies. Okay, a single set of circuit elements will be tuned to operate for a single frequency. If you are planning for eliminating multiple frequencies, you will have to use multiple such elements in parallel or in series to eliminate such frequencies. Now these passive filters can be used to suppress the harmonic currents and reduce the voltage distortion appearing across the sensitive parts or sensitive equipments. They can either inject high impedance to block the harmonic currents, if it is in the case of a uh, series connected uh, passive filter, and it can also provide a low shunt impedance path to divert the harmonic currents. So this will be this concept will be used in case of uh, parallel connected filters or shunt filters. So this can be connected in shunt or series connection, and when the filter is used in the shunt mode, it carries only a fraction of the line current, but the series filters will be subjected to full line current. So depending on the type of filters that you choose, you'll have to design the elements to withstand the voltage as well as the current which it is going to flow. It is going to pass through. Now the filters also provide additional reactive power compensation capability, which is also an additional feature when you are going for a passive filter, because you have capacitors present. So these capacitors can provide additional reactive powers to compensate for the power factor reduction in power factor due to the operation of the different loads. Now the passive filters in short can be employed to uh, remove the harmonic currents of the line or shunt the harmonic currents of the line and block the flow of current mm, among different components by tuning the elements to create a resonance at a particular frequency. So basically, resonance is what is happening here. Now, the common passive filter configurations can be seen here. So this is a single tune filter or a noise filter. You'll be having some resistance also along with this RLC series. And then here you can see that this is a first order high pass filter, this is a second order high pass filter, and this is a third order high pass filter. So here you can see that the order depends on the number of energy storage elements. Here you have two energy storage elements present. Here you have in fact three energy storage elements present. So depending on the type of the number of energy storage elements, you may have different orders, and these normally the most common is the single tuned passive filter configuration, because yeah, most dominant harmonic components will be the lower order harmonics, and you'll be able to design or tune the filter to eliminate that particular harmonic component, a single harmonic component. So this is a single tuned filter, and this will be having, it works on the principle of series resonance, where once the XL is equal to XC, you will have a low impedance path, and that provides low impedance path for that particular frequency component. Now, single tuned notch filter, as I've shown, this is a impedance carrier of a single tuned notch filter. Here you can see that R, XL, and XC. So this is a combination of RLC, and this is the impedance characteristics for a single tuned filter. So here you can see that as the frequency increases, there will be a particular frequency, for which the impedance is the lowest, and the filter offers high impedance for all other frequencies. And in particular, you can see that this particular region, where you can see that here in this region the impedance is very low, and whatever the frequencies that fall within this region, not only that FR, in and around that FR you have very low impedance. So it basically eliminates frequencies within a small band, which is basically the tuned frequency. So this is the typical the carrier of a single tuned filter, where your tuning is for a single frequency. Now, yeah, so this notch filter or single tune notch filter is tuned for single frequency or single harmonic frequency. So it normally presents low impedance path to particular harmonic current, and it is connected in shunt with the power system. And this harmonic currents will be diverted from the normal flow path, because you are having a low impedance path for the currents to flow. So all the harmonic currents will be diverted into this filter. And if you are planning to, or if you want other frequencies also to be filtered out, you will be having, or you will have to connect additional filters in parallel, so that at the point of common coupling, and so that you will be able to remove additional frequency components also, and can provide a power factor improvement in addition to harmonic suppression. And they're though they are tuned for a single frequency, they can operate for a range of frequencies in and around that tuned frequency, so that that particular frequencies near to that tuned frequency can be removed. So by providing reactive power, the notch filters also can supplement the power factor correction. Now, once you're trying to design the tune filter or design notch filter, this is designed for a single frequency, which is the harmonic frequency. So that is considered as FH, which is a frequency for which this entire thing is designed for, and F is your fundamental frequency. And in the harmonic current order that requires blocking, so in this case it is your H. So in certain cases this can be termed as N also. Okay, and the capacitive reactive power that is going to support, which is your QC, and the quality factor, which is your Q. Okay, and these are the main factors which needs to be considered. The voltage levels V, which is being taken care of here, the voltage level B, as well as the fundamental frequency F also has to be considered. Okay, now you can see that once you have the reactive, the capacitive reactive power that needs to be supplied, so that is, once that is decided, you can choose a capacitor C, because you are having and the reactive power will be supplied at fundamental frequency f. So C can be obtained from this equation, QC by 2 pi f into V square. V square is the system frequency, RMS value of the system frequency. And X, or this is rather XL. This is your XL, and this is also XL. Okay, and XL can be equal to 1 by 2 pi FHC, because this XL will be equal to XC only at a particular frequency. So that frequency is termed as the design frequency or the tuning frequency, FH. So at FH, the capacitive reactance 1 by 2 pi FHC will be equal to the inductive reactance XL. So you'll have to choose the L in such a way that your this particular condition is satisfied. So XL by 2 H into F. This is not H, actually 2 pi F. This is 2 pi F. And the quality factor can be a ratio between the inductive reactance XL as well as R. It also can be equal to XC by R, because XL is equal to XC in series resonance condition. And further, this R can be calculated as 1 by 2 pi FC. Now, the quality factor of a single element passive filter defines the bandwidth of the frequency defines the bandwidth of the filter, and it is expressed as a ratio between the reactance as well as the resistance of the filter, and the typical range is between 30 and 60. And the filters with very high Q factors are designed uh, to eliminate a specific harmonic, because so that's a norm, that's the value, that's the main purpose of this quality factor. And if the filter is having low quality factor, that means that your R is much higher. So once the resistance is very high, the other harmonic components also get reduced. So because it offers a higher resistance path. So in that way, it can weaken the neighboring harmonic components in addition to the